Hello and welcome back to the live stream. So the last couple of streams we focused on adding pointers. We can, including like dynamic allocation, pointer arithmetic and things like that. And the natural plan to go from there is to look at arrays, because then we can really test like a pointer arithmetic and all that thing. But the size of an array is a constant expression. So we need to do constant evaluation of constant expressions. So before we can do that, we first of all need to add const. And when we add const, we might as well add the other qualifiers as well. So that's the plan for today, adding const and volatile specifiers. So the standards here includes type qualifiers. We've got const, restrict, volatile, and atomic. We're not going to be looking at atomic since we don't have that. So just const and restrict and volatile. And from those, you'll first look at const and volatile because they are they are more familiar and don't less weird, so to speak. So the type qualifiers create a new form of type. This is defined over here somewhere. Here, types are unqualified, and then there are also qualified types. They can correspond to 1, 2, or 3 of const, volatile, and restrict. So let's add a new type. So to our st, we're adding a new kind of type. Let's add it to the bottom, a qualified type. So a qualified type is qualified type. It's a container. Yes, it's a container because it has like one type as a child. So it's a container, and then we've got an attribute. Like we also need to define some sort of enum and define an attribute. So enum qualifier. And there's some sort of bit field. So we've got const, volatile. Let's ignore restrict, as I said, for now. So const volatile then is const and volatile. And this is standard unit 16 is the space that we have available. So this is standard unit 16c. Then we want essentially copy something like this. So we have a private attribute, which is the qualifier t. And then we have a public getter for that, qualifier t, qualifiers, qualifier impl. Let's also pluralize this, qualifiers. And then you are qualified type. Take the qualifier and also type as its child. So this is the type that is qualified. The set qualifiers impl is we set those, and then we insert child after null pointer the child that we're qualifying, and then we also provide a getter for that. Yeah, let's just point t type yeah, qualified. Yeah, I'm unqualified. Okay, so because this returns the unqualified type. And then I need to add the enum. And so it's type node kind. We've got qualified type. This is of course this sort of type. And this is plural. Okay, So this compiles. We also need to update this code here for printing and things like that. So we want to clone a qualified type. This returns a new type that copies the unqualified type. Clone creator the unqualified type, and then we're returning qualified type for the qualifiers and the unqualified type. We don't need to look for unsigned is same, but we need to update the hasher. So the hasher for a qualified type, and we need to hash the qualifiers. And for equality, we need to compare the qualifiers. Okay. Not void, signed int, unsigned int into the scalar. Don't have an integer. Actually, they do participate here in those sort of. They might need to, like the integer rank of a type. If it's a qualified type, we might want to get the type of the unqualified version. So we probably need to adjust things there. So let's, but we'll get there when we get there. We also need to adjust this one. But for now, I'm looking for the function that prints types right here. This one. So we also want to print qualified types. So we want to print them before we print the children, and then we simply print so we want to print if type qualifiers contains const, then const. If it's volatile, then we want to print volatile. Okay, and let's just add them to the compiler and see what happens. So the standard, they are passed. The qualifiers are here when we pass type qualifiers, which are part of the declaration specifiers. So declaration specifiers are type specifier qualifier. So when we pass a declaration specifier, somewhere where do we pass those? Declaration. Yeah, a type specifier list. And here we also want to pass type specifiers or qualifiers. So they're separate here, I believe. I don't know why they're separate. Let's just add them to the type specifiers anyway. So we've got const. I know where they're. Right, and let's make them because they have a different enum values. So kb type qualifiers, symbol table, qualified type qualifier, and this maps the const keyword to qualified type const, and this maps qualified type. What am I doing? Volatile qualified type volatile. format that nicely. Well, it's not that nice, but okay. And then we also want to reserve them from, so they're not used as identifiers, type qualifiers. And when we're passing the type specifier list, we're passing a list of type specifiers, or in fact a list of type qualifiers, because they should be like let me check the grammar. Declarations. So we've got the type specifier qualifier, type specifier, it's a type specifier, type qualifier, alignment specifier, and then we've got just like a list of those. Okay. So this means that we can't just collect them as a vector. We need some variant type specifier or qualified type qualifier. I need to include the header for those. This type gets ugly, so let's just turn this one to auto. Okay. And then we need to if so this is then specifier qualifiers, specifier or qualifier. So if we're having what's it called, false alternative type specifier in the specifier or qualifier, then we are switching over the type specifier in specifier or qualifier. Otherwise, we can add a member here for the qualifiers. Zero qualified type. Let's add unqualified as a separate enum value. Qualifier t. So unqualified is just 0. And when we reach this point, we simply qualifiers. We add the new type qualifier. Get zero qualified type qualifier from the specifier or qualifier. Okay. From incomplete type. This isn't incomplete. Yeah. Probably language will probably catch up them. So qualifiers. Well, because we also want to check. So if qualifiers, so if it's already a thing, then we want to log an error, because we don't want to specify const twice. Okay, so now we're keeping track of all the qualifiers. Oh, this is, let's make this one an int actually, and then we typecast it at the end. Okay, so this now returns the unqualified type. And we want to add if qualifiers. So if we had type qualifiers, then we want to create a new qualified type. I don't think I can. Let me check how the interface looks. So right, types template create. This creates a type from the arguments. Yeah, I should be able to do that. So a CLove qualified type. And the argument are the sealer qualified type. Qualifier. So annoying typecast here. And then we got the unqualified type. Otherwise, we just return the unqualified type. Missing a comma. Need to specify a return type. Probably missing another. Oh. This should not return const, apparently. Okay, so let's try it out. We can delete those. So I want a const int x equals 42. And I got a weird error. I think I know why I'm getting a weird error. So I'm getting this error because we are attempting to link, add a child to the, right here. So we can't add the type directly because that type is already linked in the tree. So we have to create a new one. So we have to return a copy. Okay, so this means that we need to build the type. So types build, I believe, is the language server stat, so I have no idea. So I want to create a copy of the child type and return a type from there. So essentially that, but I need to use the creator interface. I'm not quite happy with this part of like the way Droid works, and now I want to clone the unqualified type. I believe that is how it works. What's the actual type? Type for is not creator. Don't make it the template, not creator. Due to the way they are interned and all that stuff, it's a bit annoying to deal with. Okay. But that's an error I can do. Now this, I'm getting annoyed with all the cast and the formatting here, and that my language server is dead. So let me restart. So qualified type, it's not the type safe thing, so let's just accept an int here and do the cast here. Just because then the call side looks nicer. I should probably, like the correct fix would be to overload the operators on the enum, so we've got proper bit sets, because this language doesn't provide them for you. And now I can do that, and now it's getting formatted a bit nice. Okay, but back to the error. So we're getting an error about an implicit conversion, because the right-hand side is an int, and the left-hand side is a constant. And currently, like CLOF doesn't know that they're essentially the same type. So assignment conversion. Actually, what does these like? Is there like a way? Like in principle, this has to be like a conversion of some sort. Although it's because of the way that they're like qualified types, probably. So the qualifier are distinct types. Any yeah, compatible type. If they're compatible type 67342. type qualifiers. Meaningful data L values. Modify, volatile, restrict, error type. Okay, doesn't appear to qualify. So I don't know how, like, the exact way to do it, but all of these conversions, like, we have a check that they're the same. I believe in principle we need we can safely ignore qualifiers here. Is the idea, I think. Like, yeah, I think let's add, where's this function used? Like, we're doing a bunch of checks for the same, but I believe in like all the places where we're doing that. So here definitely we ignore qualifiers. Here, integer promotion, we're also can safely ignore qualifiers, I guess. Here we can definitely ignore qualifiers. What is this doing? This checks that the return type. All right, this just determines whether or not we want to do a cast. And here we want to check for what does this do? Right, this does. Oh, this is the ternary operator, where we also want the same modulo qualifiers. So let's just write a new function. Rule is same modulo qualifiers. Okay, so if they're already the same type, then we return true. If qualified, so if we're having a qualified type on the left-hand side, then we're recursing with the unqualified type. And the same right-hand side. I like to use a namespace name here. Otherwise, if we're having an qualified type on the right-hand side, then we're also recursing with the unchanged left-hand side. This can never like cause an infinite loop because we're always stripping one type. Otherwise, we return false. And this is not a repeated branch in. Okay, yeah. And then let me add that. So here we want is same modulo qualifiers because we can like an expression. I guess an expression can be const qualified, but okay. So is same modulo qualifiers. Here we're doing integer promotion. So we're computing like some sort of doing the integer promotion. This does a check whether or not we want to do cast. And here we want to like we want to create a cast if the type actually isn't the same. So here we actually want sameness because if like we logically do a cast between a const qualified and a not const qualified type, so we want actual sameness. Here we want is same modulo qualifiers. Again, here we're deciding whether or not we need the cast. And then here we're doing a check that can ignore qualifiers. So let's see what that does. Okay. So we've got an integer constant expression of type 42 that is being initialized from a variable decl type x. And then we're getting an error. I'm guessing this is during closure. So let's see. Wait, why are we in? Okay. Oh, I installed debug symbols for libc, so now we're inside assert fail. Okay. I want to get, yeah, as I figured, this function we need to code gen for qualifier types. So we've got a qualifier type, and we simply want to do code gen, because by this point when we're doing code gen, like the actual layout of the type doesn't matter whether or not it's qualified. So we can just recurse on the unqualified type. Like a const int still has the same size. Okay, so this now works. I'm a bit surprised that it didn't create a cast here. I think I know why it didn't create a cast. So because we are here in do assignment conversion. And right, and we're not creating a cast expression here, which I guess it's fine. Yeah. Usual arithmetic conversions. Yeah, I guess that's fine. Let's just see. So the next thing, obviously, so we know, essentially we've got qualifiers, we're passing them, we're getting like an error if you're having multiple ones in the combination of type specifiers. We should adjust that message, invalid combination of type specifiers or qualifiers. I can make it volatile. But we obviously, like, this doesn't have any effect. So let's add an effect. So we don't want assignment. Currently, we're just ignoring that completely. And we already, so the function that we need to do is modifiable L value. So it needs to be an L value, needs to be a complete object type, and the type must not be const. Or is const. So if it's a qualified type, then we return whether or not we've got the const qualifier, else it's not const. Right, ls assignment is not a modifiable L value. Correct? It's const. Do we also handle cases like this? Yep, we do. And what about that? I'm guessing that's true. It's not a nice error message, but sure. That works. Okay, so we const has an effect. Volatile. Volatile just means that store and load needs to be visible and not optimized out. But because we're not doing any form of optimizations, currently we can just ignore that. So volatile, in effect, everything is volatile. So volatile is done. What about pointers? So we've got a const int x, and I want to create a pointer to that. I want to be able to read that pointer so I can print it, but I'm not allowed to modify it. Right, so we're definitely not handling something. Can we do that? No. Can we do that? Okay. So let's see. Right, so we're missing some case somewhere. Oh, I know what's going on here. I forgot to adjust something. So when specifying the type hashers, we need to add qualified type. Okay, so that part works, and we've got this nicely const qualified stuff here. So assign is not a modifier. L value, great. So that worked. If we remove this, this should work, except we cannot do a conversion. So because we've got an int pointer and we need to convert that to a const int pointer, but we're not allowing that conversion. So for reference, let's look at the standard. For any qualifier Q, a pointer to a non-Q qualified type may be converted to a pointer to the Q qualified type. So this part we need to implement. So if we have a pointer and the target is auto pointer, this allows to end cast from void. So if one of those is qualified, so let's get the type qualifiers of both pointers. For that, let's add a helper function. So we've got the isConst. Let's actually refactor that into a CLOAD qualified type qualifiers key type qualifiers of function, which is more flexible. So we return the qualifiers, or we return qualified type unqualified. No, unqualified. But my language was a bit dead again. Oh, because of the semicolon. Are you happy now? And then we've got an isConst somewhere. And type qualifiers of. We don't want const should be 0. Okay. And then over here we can check the qualifiers. So target qualifiers, type qualifiers of. Can I get autocomplete type qualifiers? Something is crashing my language server. I have to spend some time debugging that to figure out what exactly is causing that. So CLOAD type qualifiers of the target pointy type and the value qualifiers type qualifiers of value pointy type. Okay, and we can convert something that is less qualified to something that is more qualified. So in other words, all qualifiers present in the value need to be part of the target, and the underlying types otherwise need to be the same. So if is same modulo qualifiers, so the underlying types need to be the same. And then the qualifiers on the value needs to be a subset of the qualifiers on the target. So no const is a subset of const, which means that everything that is present in the value, so in other words, how do I check for a subset with bit operation? Let's do it manually. I'm sure there's some fancy formula to check whether all bits set in value are also set in target. But I'm not prepared to do that mental arithmetic in my head right now. So auto qualifier all qualifiers present. So if value qualifiers on zero qualify type const then all qualifiers present gleich, then we also need it in targets. Like so. Okay, and then we're doing the same thing for volatile. We also need volatile present in the target. And then if all qualifiers are present, then we return the cast. Okay. To do figure out nice bit hack to do the same. This might work. Oh, I need to. Hey, it actually worked. So we've got a pointer decal that we're initializing with like a unit expression. What the hell are you printing? So it's printing something that is totally weird. I don't know, but it's a pointer to a signed in 64. And then we're casting that to a pointer to a const signed in 64. Then we initialize it and we can use it. However, we can still not be able to modify it, right? Because we can't write to a const pointer. However, we are allowed to modify x and have this reflect in the output. Great. If I make this one volatile, I get an error because volatile isn't here, so I need to add volatile here as well. And there's a bug in my logic because this should compile. So this is volatile. And target qualifiers const volatile. So target qualifiers and zero qualified type. Volatile is 2. All qualifiers present. Oh, I need to cast you. Right, now it compiles. Because we can safely add like this extra volatile. And yeah, so that's const volatile. Let's commit that. Volatile qualifiers. Add constant volatile qualifiers. Now, something was weird with the pretty printing. Let me take a look at that. So, like the unit expression, what are they printing? Unit expression. I forgot a break. Yeah, now you're printing. Okay. Missing break in dump. Yeah. Okay. So now we've also got restrict. Restrict is a type qualifier. Where were they? Right here. So restrict is a type qualifier that can only be applied to pointers. So I think it makes sense, instead of like adding const volatile, like adding the qualified type itself to support restrict, just to add like a bit on the pointer whether or not it is restrict, because only pointers can be restrict and not other variables. So pointer type, we've got an additional attribute. Using the 16-bits, we have spare, which is a boolean restrict. Do you actually? Yeah, you need to select it. And then bool is restrict. It's restrict. And then here we've got the setter. Restrict const turn. Then we also need to hash those. Pointer type hasher. And we also need to compare it. Turn then we also need to adjust the same modulo qualifiers. It actually might make sense to keep it generic, because then we can just reuse all that, because otherwise we need to adjust whether or not, like we need to adjust here for pointers as well, and then we might want to get the type qualifiers here. So yeah, let's actually just add it to the enum. So scrap that, qualify type, we are adding restrict. There's a keyword in C++, I'm not sure. My syntax highlighting, apparently not. Let's just make it a bit weird about that. Okay, restrict is now a thing. Which means that we need to adjust a bunch of dumping codes. Here, restrict, and then we've got this horrible code that also needs restrict. Okay. And then we've got a new keyword, type qualifiers. So keyword restrict maps to clove qualify type restrict. And now we're getting a bunch of things for free. Yeah, it was definitely the right choice. For example, we can have a pointer that is now restrict. Apparently not. Because we need to adjust the parsing code. So for a pointer declarator, a pointer declarator takes type qualifiers right here, which we are not parsing. So pointer declarator right here takes, so after the star we've got an optional list of type qualifiers. And we've got already type specifier list. And so we also need like a separate list for type qualifiers. Type qualifier list. So we want to pass DSL an optional list. Let's make it not optional. Yeah, like so. So we want to pass a list. Let's not make it optional. Let's use optional one level down. A list of symbols consisting of the type qualifier table. And the value can be done very elegantly because we want to compare them with a bitwise AND. So we can fold. We can fold the that. So we can fold returning qualified type qualifier. The initial value is celof qualified type unqualified, and the operation does it bitwise or like so. And then after the pointers, we are passing optional type qualifier list. Type qualifier list. So right here we're getting qualified type qualifier. And now we're getting them this second argument. So before the child, and we want to add them to the pointer declarator. So the pointer declarator can get user data 16, qualified type qualifier, qualifiers impl, of qualified type qualifier, false, set qualifiers to those, and then we're getting within the setter, getter, I mean, so we can get the qualifiers, returning those like so, and so we then just pass them on. And when we then get the type of a declarator, we need to add the qualifiers accordingly. So we've got the pointer declarators. So if decl qualifiers are not qualified type unqualified, then we are creating so let's do it like so. So we get the type by cloning it, and if necessary, we adjust it by creating celof qualified type from the qualifiers and that type, and then returning it. Boy, that was a lot. Missing it. Right, so you here, we need to value or qualified type unqualified. This is what I've paired. Need a cast in default. What we're actually passing. So let's actually make the pointer const. Why do you still let not? Let's make it really simple. So I want to. Yeah, so that one works. Great. So we've now got a variable. Ah, you're having the wrong type. Oh, I know what's going on. Here, we don't want to qualify the pointee type, we want to qualify the result. So this one, so that, and then we want to qualify the pointer, not the type that we're pointing to. node has kind t pointer. All right, because this is no longer a pointer, this is a qualified pointer, which we need to adjust. Right. So we can't just assume it's a pointer because it might be a qualified pointer. So this means we need some sort of get unqualified type helper function. Qualifiers off. Const type unqualified type off. So it's sort of like the sibling of that function. And then so if we have a qualified type, then we return the unqualified type. Otherwise, we return the type itself. And then in CodeGen, or wherever we were with that assertion, this was in the compiler. So we need to strip the type qualifiers first. And then we also need to is valid type. So dref, we want a pointer. I'm guessing logically speaking, a qualified type is still a pointer. So let's take this one. This is not consistent with everything else. So let's unqualified type. So the unqualified type must be a pointer. We need to use unqualified types here for everything, except for so unqual type. So because this one can safely have qualified, this one, this one, this one, this one, this one. So we ignore qualifiers when checking for the operations. So this now works. We're now having a const pointer to non-const int, which means this one is not allowed, but this one is. Right. Okay. We probably need to do these fixes for the binary expression as well. Arithmetic. What again? This is a cast. Yeah. We need like a bunch of types that let. Okay. So we need to go over here and fix a bunch of cases where we need to check the unqualified type. So let's go through it one by one. This one doesn't matter. The cast expression. You know, unqualified type of. Yeah, I need to like. I'm doing it slightly different, so I think it's fair to just strip qualifiers from all of those. So let's go through this type queries one by one. Of unqualified typo. So we only need to adjust at the unqualified types. Okay, so now we're probably stripping all the qualifiers, which means that we're actually doing the correct conversion here. I can do the correct operations. Okay. This was actually a bug fix. So let's do fancy commit. I don't want to restrict yet. I want this one. I do want this one. 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 Not this one. Not this one. Not this one. This one. This one. This one. This one. Support qualifiers on pointer type. Okay. So now back to restrict. So currently restrict is just a qualifier, just like volatile, it doesn't do anything. However, restrict does something. So restrict does something that is defined here. Yeah. So restrict means, there's an example here. That it tells the compiler that the pointers are restrict, which means that P and Q will not point to the same thing. So they essentially don't point to the same object at the same time. And this can be used to do optimization. And there's this clause here. Translator is free to ignore any or all aliasing implementations of use of restrict. So in a way, we've correctly implemented restrict fully according to the standard. They're similar to volatile, except that we don't handle volatile completely. We need to do something later on. But for restrict, we can just ignore it. This is a bit unsatisfactory, but it makes sense because it is used to do optimizations. However, restrict can do undefined behavior, right? So if they do overlap, then the program has undefined behavior. And it would be nice to check that somehow. However, that is not trivial. Right, here's an example. This call is valid, this call is undefined behavior, because they overlap. And it would be great if we were to check that. I don't think it is possible with Love's model right now. So adding restrict in a way, yeah, it's probably not implementable in an easy way, and definitely not in the time I've left today. So let's just commit that. And restrict qualifier currently does nothing. Although we should implement the check that we can't restrict normal variables. Why are we crashing when we do that? That's a bit weird. Because we're assuming the target type is, we need the unqualified type. Right here. So we need to put the unqualified types, and then we're getting like weird implicit conversions error, which is because we have pointed to restrict, which is actually like really funny, because we can fix that by making this one restrict as well. But this is nonsense. You're not allowed to form restrict for non-pointer types. So when we add the, essentially every time we create CLOUP qualified type, we need to check that right here, no, not right here. Right here, we need to check that the type itself isn't a pointer. So if qualifiers include CLOUP qualified type restrict and the type is not a pointer, the unqualified type, then we log an error. And the same thing when we create pointer declarator somewhere over here. Get type. Here by definition we don't need to check whether or not we apply restrict, because we're always creating a pointer, so we don't need that check. So that works out nicely because we can't report errors here. So invalid combination of type specifiers or type qualifiers. So now we properly implemented restrict. Okay. So let's end the stream here. Thanks to everybody who stepped by. And next week we will tackle constant evaluation and const expr in C, because C23 is going to add const expr. So let's implement that next time.